In the meantime, I'm going to introduce our third speaker, Christopher Ghosh, who is working with Interchain Foundation, and he's going to talk about sovereign to sharded, the shared security spectrum.
That's right. Thanks for the introduction. Happy to be here. It's fitting that the first two talks were on interchain communication and then sharding, because I'm going to talk about something that incorporates both of those, but is not quite the same as either. This is sort of early research in progress by Interchain GmbH, by the ICF, in collaboration with Informal Systems and APFL. And partially I'm giving this talk because I think it represents a design direction that has not yet received a lot of focus. So in part, I want to inspire people to take up what I'm going to call the shared security spectrum. So I work at Cosmos on IBC, or the Inter-Blockchain Communication Protocol, which has been more or less recently finished and is now in final testnets prior to deployment. But what I'm going to talk about now is a little bit different. I'm going to talk about the next steps beyond the deployment of IBC, beyond the deployment of some of these sharded systems like Polkadot and Near, what kind of interchain topology we see emerging, what kind of constraints that brings up, and what kind of security guarantees users will want to reason about when they're executing cross-chain transactions, and how we might be able to help out. So my central contention in this talk is that so far there have been two extremes in the design space that have been pursued. Extreme one, I call sovereign validator sets. Those are systems where, say, two chains or two distributed ledgers have completely disjoint validator sets. So usually I'm talking about proof of stake or proof of authority, some similar reasoning and price to proof of work. But at this point, most of these systems that I'm talking about are proof of stake, and I'll use that as the candidate example. So sovereign validator sets are not overlapping. That's one extreme that's been explored by Cosmos. It's explored by sort of different chains with respect to each other. I'll get into more detail on that in the next slide. The next extreme is shared validator sets, or sharded systems. And the mechanisms of sharding vary. What kind of, as was mentioned in the talk just prior, there are different ways of figuring out which nodes are supposed to participate in validation of which shards when, and those have different advantages and disadvantages. But all of these approaches have in common that they have some known set of shards, known set of nodes, and they're allocating nodes to shards or allocating shards to nodes, one or the other. Then I'm going to argue that there's, in fact, rather than two options, a spectrum in between, where we have partially sovereign validator sets, some overlap, not total overlap. But if we allow the chains to reason about the overlap, we can perhaps both give the chains themselves and users of those chains in a cross-chain message passing context some useful guarantees. So I'll outline what kind of architecture that requires, what kind of cross-chain message passing needs to be taking place, what the chains need to reason about, what kind of heterogeneity is still possible, what kinds of common requirements have to be satisfied. I'll talk about different thresholds of overlap, which provide perhaps different guarantees or trade-offs of interest. I'll talk about then what kind of dynamic routing would need to be employed by users using a multi-chain network, and a speculative venture of what sort of dynamic shared security protocol could allow different chains to coordinate to provide better routes to users, and finally talk about what research we're conducting and next steps. So the first end of the spectrum, as I alluded to already, is sovereign security. And this is the model used initially by Cosmos. It's also the model you can think of different chains, completely separate chains, using different code bases, different consensus algorithms, but having some kind of cross-chain message passing in place as using with respect to each other. So in sovereign security, each chain has its own validator set. There may be intersections, but they are not known to the protocol. There's no topology. There's no like global view of the topology, right? And the chains, even if they're communicating with each other, aren't reasoning about any sort of equality between their validator sets. They're just disjoint. These chains may be completely heterogeneous, but in practice, there are often commonalities. With proof of stake, they're almost always using some variant of BFT consensus. Maybe there are bridges in between these chains, but there's also cross-chain message passing going on, and users who are sending messages from one chain to another and care about the security they're getting when they're doing so. On the right end of the spectrum, we have shared security. The basically defining characteristic of shared security is that there is some set of shards with which you have a global view of what validators are where. So the allocation mechanism here can vary. It could be node to shard to node, but you have some validator set, some shard set, and they are matched somehow, and you have this set fixed topology. Using this fixed topology, the shards themselves, and perhaps a special coordinating chain, if that exists, can reason about what kind of inter-shards message passing is possible and what kind of safety guarantees it has. So examples of this include Polkadot, ETH2, Near, various derivative designs thereof of those systems. And so far, sovereign security and shared security have been the primary venues for design exploration, both in the literature and in practice. But if we start to look at what these chains actually look like in practice, these are on the left and the right here, a snapshot of the, I guess the top 20 validators for Cosmos, the Cosmos Hub blockchain on the left, and the top 16 or so validators for Near on the right. And if you look down these lists, you'll see that, in fact, a lot of these validators are operated by the same people. We can look at Dokia Capital, we can look at a Zero Knowledge Validator, Chorus One, Figment. There's a lot of overlap here. Now, when we reason about BFT consensus in the abstract, we're usually talking about some fixed set of nodes or set of nodes with variable voting power, and we have some notion of identity as a public key, and we talk about fault thresholds with respect to that voting power and that identity. But in practice, if we think about what kind of operational infrastructure is actually in place, these are legal entities. Maybe they have servers set up in some data center. They have specific signing infrastructure. Perhaps they could be bribed. And when we're reasoning about proof of stake security in practice, probably the closest thing to what we're trying to reason about is the identity of the operating entity who has the sort of control over whether or not their validator and their signatures follow the protocol or contravene it. So if we look here between these two chains, which are unrelated with respect to each other, the Cosmos Hub is a sovereign chain and Near is a sovereign chain. They don't have any sort of inter-sharding protocol going on, but they're very interested in cross-chain communication, and they could both use something like IBC. There's a lot of actual overlap between the validator sets, but because the protocol can't reason about it, it can't provide any guarantees based on that overlap. So for this reason, I think we should start to consider the spectrum in between sovereign security and shared security. And here is kind of a fuzzy area where we have partial but not necessarily complete validator set overlap. So maybe there's some thresholds here that matter. So maybe there's a third of validators in common, 2/3 of validators by stake in common, maybe less, maybe more. But if we give the protocol the ability to reason about that overlap, to identify validators across two chains, then we can start to provide useful guarantees, as I'll get to in some of the next slides. The specifics of this may vary because we're dealing with heterogeneous chains. They might use slightly different consensus algorithms. Mostly here I'm talking about proof of stake using BFT. But there's not necessarily any sort of common validator set management. There's no master chain between Cosmos and Near. However, they do have the ability to communicate with each other. In order for this to be interesting, you want a situation in which, or the situation we're talking about is where there are users who are sending cross-chain messages over some kind of bridge between the two involved chains. And in the simplest case, this bridge is based on the security model of the chains themselves. So in the case of IBC, this means the chains are running light clients for each other. So the only signer sets we're reasoning about are the validator sets of both chains. We don't have a separate set of signers for the bridge. You could still reason about this. You could have a similar kind of argument to what I'm going to make here. If you had a separate signer set for the bridge, it's just a little bit more complicated. So the basic architectural requirements in order to allow chains to reason about the overlap between their validator sets is that we have some, at least roughly architecturally compatible consensus so that it makes sense to speak of nodes behaving correctly on both protocols. This probably means proof of stake BFT. So we have something like the usual greater than 2/3 honest node assumptions. Proof of authority can also work, but that's pretty rare in practice. The minimum specific requirement we need is that the two chains need to be able to reason about when validators are the same. And what the same means is kind of up to the kind of security requirements you want to be able to talk about. But probably what we're going to be looking at here is a validator on one chain choosing to identify itself as the same as a validator on another chain. So in the example I gave 2 slides ago, Bison Trails or Adokia Capital could sign over their signing key for one chain with the signing key for another chain and thereby identify themselves as the same validator on both chains. More complex options are possible. This is the subject of some of the research we're conducting. It's possible to also split parts of the proof of stake system across chains, again, in something that is not quite sharding, but a little bit in between sharding and sovereign security. But that's not necessary for the kind of message passing guarantees I'm going to talk about here. It's just convenient for other reasons, like making it easier to recruit a validator set. So if we think about being able to reason about the overlap between validator sets in a cross-chain message passing context, what does that buy us? I'm going to start off with a simplified case, and then I'll cover more complex cases. So in the simplified case, we have two chains. They're running BFT consensus, and we have the usual greater than 2/3 honest assumption. So let's think about what we can reason about, what kind of guarantees we have if we know different levels of validator set overlap between those chains. So if we start with the assumption that both chains have 2/3 honest, and we know that they have 1/3 overlap, then we know that they're at least going to have one honest node in common. So then we know that there's at least one honest node which has common data availability of, say, transactions which were committed to both chains. If we know that there's greater than 2/3 overlap, then we know that there's greater than 1/3 honest nodes in common and greater than 1/3 nodes with common data availability. And this level of overlap is particularly interesting because it means that you can safely introduce from the sort of without introducing any new security assumptions, you can provide guarantees about cross-chain latency, which is otherwise not possible. So if you think of two chains with disjoint validator sets where you don't know anything, they're operating completely on their own logical clocks, messages can take forever between the two chains. But if you know that there's at least 2/3 overlap between the validator sets, then you have at least 1/3 honest nodes in common, which means that the honest nodes in common, at least one of their votes is required for the chain to progress, as we're working in a BFT context. So this means that you can tie, if you want to, you could tie progress on one chain to progress on another chain. And if you introduce, say, slashing rules for delay of cross-chain messages, then because you have this level of overlap, you know that the nodes are going to be able to comply with those rules, which means it's safe to introduce them. So that's the simplified case. But in practice, we're probably going to be dealing with a more complex topology, not just two chains, many chains connected, and users are going to be sending messages across many chains at once. So I'll talk about 3 chains and then n chains, but these properties basically generalize. So if you think of 3 chains, let's say we talk about 3 chains ABC. Again, they're running BFT consensus. Again, we have the same 2/3 honest assumption. If we have the 1/3 overlap between the 2 chains, we have a 1/3 overlap between A and B and a 1/3 overlap between B and C. The pairs A, B, and BC are guaranteed overlap with one honest node, but A and C, of course, are not. However, B can relay messages between A and C. And if we're using a message relay path which incorporates this information about overlap, then we can sort of recover the guarantees we got from the simplified case of 2 chains, even in the case of more chains, when the sort of ends of the path, as it were, don't necessarily have this amount of overlap. So then if we're talking about 2/3 overlap in the 3-chain case, where A has at least 2/3 overlap with B, and B has at least 2/3 overlap with C, the pairs AB and BC are guaranteed 2/3 overlap. The pair AC is guaranteed 1/3 overlap. So AC is guaranteed 1 honest node overlap. But of particular interest, if we talk about message relay happening between A and C, but through B, then through this intermediate B, we can get this kind of latency guarantee, which we can't actually get directly for A and C. So because A and C don't have this 2/3 overlap, we don't have a guarantee that A and C have a 1/3 honest node in common, and we can't, say, impose, we can't guarantee cross-chain latency bounds, cross-chain message passing latency bounds between A and C, because they're potentially proceeding completely independently. But because B and A have 2/3 overlap and B and C have 2/3 overlap, if we instead relay a cross-chain message from A to B and then from B to C, in both of those hops, we can have this kind of latency bound, and so we can add the latency bounds together, basically. And we end up getting this latency bound for messages which are relayed from A to C through B, which we couldn't get if we relayed directly from A to C. Now, this starts getting really interesting when you think about the arbitrarily complex case that we're much more likely to see in practice, which is that we have some very complex graph of chains. Many of them are connected to each other. Luckily, we don't need to reason about the whole graph at once. We just need to reason about the path on which a user is sending some kind of cross-chain message that they care about. So here we have n chains. They're arranged in any topology. We'll just call them C1 through Cn. Same assumptions as before, BFT consensus, 2/3 honest assumptions. These are like the assumptions the protocols are using anyways. We're not introducing any more assumptions. If you wanted to use these chains, you're already making this safety assumption in the case of BFT proof of stake. So if we think about the generalized case of this cross-chain message passing path, if we have some path between C1 and Cn, where all hops have 1/3 overlap, that is to say C1 and C2 have at least 1/3 overlap, C2 and C3 have at least 1/3 overlap, C3 and C4 at least 1/3 overlap, etc., through Cn-1 and Cn. Then if we use as a message relay path this path where we have at least 1/3 overlap, then we know that there's at least one honest node in all components of the message path. And analogously, if we have all hops having at least 2/3 overlap, then we know that all components of the message path have at least 1/3 honest node overlap. And we can relay messages between C1 through Cn with these kinds of latency guarantees. Again, because even though C1 and Cn at this point might not have any nodes in common at all in their validator sets, but as long as all of the individual hops have at least 2/3 nodes in common, then we can provide a latency guarantee for each hop and add them together to get a latency guarantee for the whole message passing route. So how might this be used in practice? If we think about a multi-chain topology, users are going to be interacting with this topology to send messages over IBC or over some set of bridges. And they need to select a route when they're sending a message. And we're sort of, different use cases are going to have different requirements. There's some trade-offs here. So I just talked about what kinds of thresholds, if you have a route which has a sufficient overlap on all of the hops, what kinds of thresholds give you additional guarantees, which may be useful. But those do come at, they aren't free, they come at a cost. In particular, a cost that will probably increase some proportion to the number of hops. So we're in this topology here, these hops we're talking about like a space of overlap between validator sets. So if you were to, unfortunately, I don't have a graph here, it would be easier to visualize, but if you were to imagine these chains arranged on some kind of graph where distance in the graph represents not some sort of latency, but actually represents validator set overlap, then your paths are going to be paths through that graph. But of course, that distance is validator set overlap. It's not like distance in geospatial coordinates if there were blockchains running in different corners of the world. So you're probably going to pay in latency when you add more hops. So if like n is really large, you're going to have some additional delay with each hop you add. And probably costs in terms of transaction fees that you have to pay. But if you as a user are trying to dynamically create a route, you have basically the option to choose how many hops you're willing to pay for and willing to tolerate latency-wise. And if you allow more hops, you're much more likely to find a path of higher overlap. So if we assume some like stochastic distribution of validators over these different blockchains, then the more hops you allow your message routing algorithm to find paths with, the more likely you are to be able to find a path that has at least the requisite overlap on all of the hops. The other little tricky bit, especially with regards to implementation, is that all of these validator set overlaps are potentially changing dynamically. So if we're talking about most of these proof of stake protocols have the ability to update their own validator sets. Some of them do it instantaneously or per block, like Cosmos. Some of them do it on some epoch schedules, like every day they'll update the validator set. So this means that if you want strict guarantees as a user, you need to either lock your message, like hash lock your message to a particular validator set, and it gets returned and reverted if the validator set changes, or you need to rely on epoch timing and then ensure that your message will get delivered before like the epoch changes, before the validator sets change. Now, this routing can be performed either on-chain or client-side. So the chains themselves, because they already can reason about the overlap, like I mentioned, they also will have the ability to reason about what kind of route they need to create. Maybe they won't the whole topology, but they might know part of it. That means that light clients could use this light client information to potentially dynamically route messages according to some preferences provided by the user in the message when it's being sent around, but it's also possible for the client to do the whole thing client-side. Different use cases probably are going to have different latency, costs, and security requirements and trade-offs. So dynamic routing is probably likely in practice. Dynamic shared security is the much more crazy idea, but I think it's based on a sound sort of assumption on how the topology is going to evolve, which is that there will be different chains which are used for different things, and users probably want fairly frequently to relay their assets between different chains and use different chains, within the context of a single, like a gestalt application with state on multiple chains, or a single intended user flow of transferring funds between different things, etc. So in order to better fulfill what users want, which is the ability to do this safely and cheaply, it would be possible for validators and blockchains to both agree to give up a few degrees of freedom and allow the topology to be optimized a little bit for in order to provide better paths for cross-chain message routing for users. So what would this look like? This would look like validators choosing a common identity, so a way to assign themselves signing keys on all of these different chains, and validators choosing what kinds of stake they're willing to put up, a set of chains they will validate, but not specifically assigning specific amounts of stake to specific chains. Chains then would choose what staking tokens are allowed and what rates those staking tokens translate into voting power on that particular blockchain. Then there would be some common algorithm, which doesn't require sort of giving up sovereignty in the traditional sense. There doesn't need to be a master coordinator, but this is just an algorithm that these chains run independently that would match up validators and chains in accordance with their preferences. They need to coordinate on the edges a little bit, but they don't need to coordinate in a central location. And then this would sort of use these degrees of freedom, which the validators and chains are giving up, to optimize in order to create message paths with more overlap and preferably fewer hops for the overall topology. Now, in order for this to work, in order for validators and chains to agree to it, it needs to be matched up with the crypto economic incentives in play, which will probably be tricky, but there are, if we assume that this is what users want, it's a reason to consider it from the design perspective. Now, at the moment, it's going to be very difficult because it requires coordination between different token holder sets, which right now are mostly thinking about their own chains. So the main takeaways I want you to get from this talk are that validators that overlap between chains in a cross-chain message passing context is really useful. And it's something that we want blockchains to be able to reason about, as opposed to just having these two extremes of sharded systems and sovereign systems. There's this whole spectrum in the middle where we have some amounts of overlap, not total overlap. As we can see in practice, there already is a lot of overlap anyways, even without protocols to detect it or incentives to facilitate it. It just so happens that the people who choose to run validators for one chain, for example, like their infrastructure costs consist of some flat cost plus some scaling cost. And so it's cheaper on margin to add new blockchain. So there will end up being a lot of correlation between validator sets of different chains. We should open up this overlap in the protocol to allow protocols to reason about what kind of overlap they have with other chains, and then provide better safety and latency guarantees to users who are using those chains in a cross-chain message passing context. Even with enough overlap, we can get guarantees such as like latency bounds, which are pretty similar to what kinds of guarantees you have when you're dealing in a complete shared security context with a validator set managed by a coordinator or with a fixed or known topology. The second takeaway is that multi-chain topology optimization, especially from the crypto economic perspective, is a general problem, and a problem that we should be taking seriously if we expect users to be using a lot of chains frequently. Chains are mostly in the design of proof-of-stake protocols worried about their own incentives. They consider themselves as a closed system with validators and users and maybe even the shards, but that's not what users are thinking about. Users are thinking about the multi-chain ecosystem. And in order to, these sort of chains need to coordinate together at the edge in order to give up a little bit of their degrees of design freedom or agree to crypto economically share the costs for providing better multi-chain topologies for users to use. Now, the desiderata of what different use cases require in terms of security and latency or costs are still pretty unclear. These protocols are still in the nascent stage. Some bridges are in production. Many things are in testnets. Probably it will take a year or two before we have, many concrete data points on what kinds of multi-hop cross-chain messages are being sent. But the analyses of the protocols can and should proceed in parallel. And bounds can already be provided as to what different levels of overlap would provide in terms of guarantees, what kinds of optimizations are possible in a multi-chain context, etc. I also think this is a great area of research for collaboration between different foundations, different projects and researchers in the space. Insofar as we need the blockchains to collaborate in practice, we also should ensure that the research teams are collaborating in theory. And I encourage anyone who's interested to reach out to me at CWGoes at Interchain Berlin. I'd love to take questions.
Yeah, so I have a small question. If you are a validator of multiple chains, it's natural that there will be fluctuation in the price of your tokens and your value. How would that play a role when the security is bound on the fact that you are a validator in 2 or 3 chains? Is this something that you've thought about, modeled?
I'm not entirely sure I understand the question. You're talking about if I'm a validator of one chain, I might only be thinking about my rewards on that chain? Or?
Yeah, or let's say that there is a fixed amount of money we want to throw at the cryptocurrency. Maybe I want to kill one chain because then my other chain that I have more stake in will get more value. Is that an incentive that makes sense?
I see. That's certainly possible. I mean, I would say that's a different area of research. We're more thinking about what happens when maybe a proof of stake, there could be reasons for chains to want to attack each other, or there could be reasons for users to try to double spend in the context of these cross-chain protocols, and validators, or users of validators to try to double spend, and validators might, for that reason, want to purposefully equivocate or bribe another validator to equivocate. I mean, I think in terms of the sort of crypto economic design problem, it's a matter of translating what the users of the Gestalt system as a whole actually want and thus are willing to pay for into the right low-level structure. So that's why I talk about users wanting safety in a multi-chain topology, because if users want safety in a multi-chain topology, they should be willing to pay for it. And that fee is going to be split between multiple chains in complex ways. But if those chains can figure out a way to collaborate on the crypto economic incentives to split the fee and to optimize their validator set distributions to provide better cross-chain message pathing, then that should end up being profitable for them because users are ultimately willing to pay the fee for that level of security.
Is there a reason this multi-chain won't collapse to one chain?
Certainly. I mean, in theory, the reason is mostly scaling. In practice, it's also the fact that different chains end up specializing in different things. Their state machines evolve to facilitate different purposes. And there are disjoint, and in particular, there are reasons to want sovereignty. I mean, if we think about a global blockchain, or if you're using a global blockchain with 100 validators around the world, then the security of your payments network is dependent on a lot of geopolitical context, which is out of your control. Whereas if you have a local blockchain in your city or in your state or something, it's much more aligned with the sort of external incentives of the people who are providing validation and using the blockchain, etc.
Cool.
It would be possible to formalize that if you had some notion of the external incentive alignment between parties who are participating, because ultimately the state on these blockchains is tied to some real world value. Otherwise, they wouldn't be useful. And you also want alignment on whatever the real world value is.
Yeah, that's definitely interesting. And I think there's a lot of room to answer those questions. So thank you very much, Christopher.